How are you all doing this morning?
Good.
All right, well, today we are going to be talking about second order filter circuits. Don't know that this will take a full hour and 15 minutes, but we shall see. So let's start with this guy, where we have an inductor L in series with some capacitor C. And then we are going to take the voltage drop over our resistor R as our output signal. And as per usual, we will apply our input voltage here on the left. So our transfer function for this circuit, H of omega, is going to be R here in the numerator, and then we're going to have R plus J multiplied by omega L minus 1 over omega C, where that imaginary part is just a series combination of the impedance of the inductor and the impedance of the capacitor, where I am explicitly saying that the impedance of capacitor 1 over J omega C is the same as negative J over omega C. So what I'm going to do now is I'm going to multiply this guy by omega C over omega C, and that is going to give me omega RC divided by omega RC plus J times omega squared LC minus 1. So that is my simplified version of the transfer function. So now what I'm going to do is I'm going to split this guy out into its real and its imaginary components. So I'm going to do that by multiplying this function by the complex conjugate of the denominator over the complex conjugate of the denominator. So I'm going to have something that looks like this. So I'm going to have omega RC minus J times omega squared LC minus 1 here, and that exact same thing in the numerator. And let's see what happens when I do that math. So I'm going to have omega RC quantity squared here plus omega squared LC minus 1 quantity squared here. Then I'm going to have omega RC quantity squared minus J omega RC omega squared LC minus 1, which will look like omega RC quantity squared over omega RC quantity squared plus omega squared LC minus 1 squared minus J omega RC omega squared LC minus 1 over omega RC squared plus omega squared LC minus 1 squared. So we have our real part and our imaginary part explicitly written out. So now we can find our magnitude and our phase angle. So for our magnitude or our frequency response, we're going to have the square root of the real part squared. So that'll be omega RC quantity squared over omega RC quantity squared plus omega squared LC minus 1 quantity squared, this whole fraction squared, plus negative omega RC omega squared LC minus 1 all over omega RC squared plus omega squared LC minus 1 squared, square this whole thing, take the square root, and let's look at our denominator first. Is probably going to be the easier part here, right? So it's going to look like omega RC quantity squared plus omega squared LC minus 1 quantity squared, and then this whole thing gets squared. So we have that as a common denominator. For our numerator, we are going to have omega RC squared plus omega RC squared omega squared LC minus 1 squared. And I wrote it out in that odd looking form so that we can pretty easily see. No, sorry. Computer's doing weird stuff having to do with Java right now. Don't know why. To my knowledge, I'm not using Java for anything. So our denominator will be omega RC squared plus omega squared LC minus 1 squared, that whole thing squared. I'm going to factor out an omega RC squared from this guy. And so what that's going to give me is omega RC squared times omega RC squared plus omega squared LC minus 1 squared. And this guy cancels out one of these powers, leaving us with a square root of omega RC squared plus omega squared LC minus 1 squared in our denominator, and we just have an omega RC in our numerator. Let me more clearly write a 2 there. So if we evaluate this expression at omega is equal to 0, we're going to wind up having 0 in the numerator. When omega is 0, omega times RC is obviously 0. And then we'll have the square root of 0 plus 0 minus 1 squared. So we'll have 0 over negative 1 squared, which is going to be 0 over the square root of positive 1, or 0. So at low frequencies, all of our signal is attenuated. At very high frequencies, we are going to have infinity divided by the square root of infinity squared. Actually, hold on. So let's look at this guy, right? So our numerator is going to be infinity, and then we're going to have the square root of infinity squared plus another infinity squared, which would be infinity over the square root of twice infinity squared. I know this is going to sound a little odd here. Oh, I take that back. Okay, sorry, I made a mistake here. So the mistake that I made, we have omega squared squared, so this should be infinity to the 4th power. Okay. So that means we're going to have infinity over infinity squared, approximately infinity over infinity squared, which should roughly look like 0 at very, very large frequencies. So at very low frequencies, all of our signal is attenuated, and at very high frequencies, all of our signal is attenuated. So this is a bandpass filter. So the response for this bandpass filter, as a brief review of what we talked about last Friday, it's going to look something like this. Here's our magnitude, response as a function of frequency. So ideally, it's going to be something like this, where this is our pass band. The pass band begins at omega low, it ends at omega high, and in the middle there we have some resonant frequency, omega naught. To the left, everything below omega low is considered stop band, and everything above omega high is considered stop band. This is the ideal case. For our practical circuit, it would look something more aligned with this. Where if this value is 1, this value is 1 divided by the square root of 2. That's the 3 decibel frequency. Put it out here as minus 3 dB. And so omega low and omega high still represent our effective cutoff frequencies for our filter. When we solved for our cutoff frequency in class on Thursday, it was fairly trivial because there was only going to be one answer, right? So what I'm saying is if we tried to make this guy right here exactly equal to 1 over the square root of 2, it's going to be significantly harder to do it now because we have multiple squared terms and all that kind of good stuff. So instead of us doing the rigorous mathematics that are involved, I'm really just going to give it to us, okay? So omega low for this series RLC circuit will be negative R over L plus the square root of R over L squared plus 4 omega naught squared. I'll tell you what omega naught is in just a second. Divided by 2. Omega high will be positive R over L plus the square root of R over L squared plus 4 omega naught squared divided by 2. And omega naught, hopefully this won't be much of a surprise, is simply going to be the square root of 1 over LC. So omega naught for a series RLC circuit that we're using as a filter is the exact same thing as omega naught for a series RLC circuit that we were doing transient analysis on, because they represent the same thing. It's the resonant frequency of the circuit. We could actually, if we rolled that factor of over 2 into our expression for omega low and omega high, so I'll do this in pink, we could recall for series RLC, alpha was R over 2L and omega naught was the square root of 1 over LC. From this, omega low is simply negative alpha plus the square root of alpha squared minus omega naught squared. And omega high is simply positive alpha plus the square root of alpha squared minus omega naught squared. So these cutoff frequencies are very similar to the natural frequencies of the transient response, but instead of changing the sign on the plus or minus sign or associated with the everything under the radical, we're changing the sign on the alpha out in front. Other than that, it's exactly identical to what we did with our transient analysis of RLC circuits. Another quantity that I'd like to discuss is what's called the bandwidth. So the bandwidth is simply the range of frequencies over which this circuit is able to pass signals. So the bandwidth is defined as omega high minus omega low, which is going to be negative R, or excuse me, positive R over L divided by 2. Minus negative R over 2L is simply R over L. So that's our bandwidth for the circuit. So we actually now have enough knowledge to construct a very rudimentary circuit that could tune into a specific radio frequency. So, for example, anybody know what the the frequency for Louisiana Tech's college radio station is? ALPI. It's the radio station run out of the student center. Anybody have any idea? All right. Well, here on Tech Campus, we have a radio station that broadcasts on the FM band at 89.1. So what that really means is that it's broadcasting at a frequency of 89.1 megahertz. So this would be omega naught, or really it would be omega naught over 2 pi. I guess I should state that explicitly. And the FM radio band has a channel separation of 200 kilohertz. So it has a bandwidth of 200 kilohertz, which means that omega low over 2 pi is going to be (89.1) megahertz minus 100 kilohertz, or 89.0 megahertz, and omega high over 2 pi would be 89.1 megahertz plus 100 kilohertz, or 89.2 megahertz. So we have all the information that we would need to design a filter circuit to be the tuning portion of a radio that would pick up only that radio station while attenuating all other radio stations along the FM frequency band. In fact, analog radios, this is literally how they work. And you have a fixed bandwidth of 200 kilohertz because you always need a bandwidth of 200 kilohertz for FM radio. And then you change the frequency that you're tuned into by changing the capacitor value. So you use a variable capacitor to allow you to tune over a range of frequencies with that fixed bandwidth that's established by the resistance divided by the inductance of the circuit. So you guys now have at least some small idea of how a significant portion and an integral portion of a radio works. All right, so circling back around, our phase response okay, theta h as a function of omega is the inverse tangent of the imaginary portion. So let's scroll up and figure out what that was. Omega RC over, oh, excuse me, omega RC times omega squared. Omega RC, omega squared LC minus 1 divided by omega RC squared plus omega squared LC minus 1 squared. Our real part is omega RC quantity squared divided by that same denominator, omega RC quantity squared plus omega squared LC minus 1 squared. Our denominators cancel each other out. This guy right here lowers the power of this guy by 1, and we're left with the arctangent of omega squared LC minus 1 divided by omega RC. So that's how our phase response behaves. Next, I'd like us to look at this circuit. We have a resistor R. Now we have our inductor L in series with our capacitor C, and we are going to take the output voltage over that series combination of inductance and capacitance, right? So call this J omega L and negative J over omega C, dealing with the impedances explicitly. And we get a transfer function of J times omega L minus 1 over omega C divided by R plus J times omega L minus 1 over omega C. If we multiply through by omega C over omega C, this gives us omega squared LC minus 1 in the numerator and omega RC plus J omega squared LC minus 1 in the denominator. So this is our simplified form of our transfer function. To break it down into its real and imaginary parts, we'll have to do what we just did. Just multiply by the complex conjugate of the denominator over the complex conjugate of the denominator. So let's see, omega squared LC minus 1 omega RC plus J omega squared LC minus 1 multiplied by omega RC minus J omega squared LC minus 1 omega RC minus J omega squared LC minus 1, and what we are left with is a denominator of omega RC squared plus omega squared LC minus 1 squared. So the exact same denominator we had for our last circuit. And here we are going to have omega RC times omega squared LC minus 1 as a real part, minus J omega squared LC minus 1 quantity squared as our imaginary part. And I'll just explicitly break this up. Omega RC squared plus omega squared LC minus 1 squared. All right, so our magnitude is going to be the square root of the real part squared plus the imaginary part squared as per usual. So we'll have omega RC omega squared LC minus 1 divided by omega RC squared plus omega squared LC minus 1 quantity squared plus negative omega squared LC minus 1 squared over omega RC squared plus omega squared LC minus 1 squared and we are obviously going to have a denominator of omega RC quantity squared plus omega squared LC minus 1 quantity squared, that whole thing squared. In our numerator, we are going to have omega RC squared times omega squared LC minus 1 squared plus omega squared LC minus 1 squared. So there's a common factor of omega squared LC minus 1 squared that I can take out. Omega squared LC. So this is going to be multiplied by omega RC squared plus omega squared LC minus 1 squared. This guy cancels out 1 power of that, leaving us with omega squared LC minus 1 divided by the square root of omega RC squared plus omega squared LC minus 1. So when omega is equal to 0, this guy so when omega is equal to 0, it's going to look like -1, because we're going to have 0 minus 1, so that's -1 over the square root of 0, so that part doesn't matter. So -1 over the square root of -1. Did I make a mistake with the sign somewhere? Because this should wind up looking like 1.
I think the omega LC minus 1 in the square root needs to be squared.
You're right. You're absolutely right. Thank you. Okay. So -1 over the square root of 1 is going to look like -1. But when we take the magnitude of it, so here's where we're going to have a little bit of a pickle per se. We're explicitly ignoring negative frequencies, which mathematically exist, but in practice do not, right? So if we evaluate this guy at omega is equal to 0, we're going to get -1 over 1, which is -1, taking the absolute value of that so that we're only dealing with positive quantities. Oops. No, yeah, that's the right thing. Is going to give us 1, but I'm going to put it as the absolute value of -1. When we work at infinity, we're going to have infinity squared over the square root of infinity to the 4th power, which will be infinity squared over infinity squared, gives us +1. So what this guy is a band stop filter, right? So as a brief review of what we talked about on Thursday, a band stop filter looks something like this. So here is the absolute value of the frequency response. Here is frequency. So we're going to have a pass band. Something that looks like this, where both of our blue regions are pass band. And the edge of this first pass band, where it transitions from passing to attenuating, is omega low. The edge of our second pass band, so where it goes from attenuating everything to passing everything, is omega high. Right in the middle, we're going to have omega naught. So this region in the middle is our stop band. Call this a band stop filter? Yeah, just making sure. And in a practical case, it's going to look something like this, where these transition frequencies, if this is 1, this is still going to look like 1 over the square root of 2. And we will see that omega naught is square root of 1 over LC. Omega low is negative R over L plus the square root of R over L squared plus 4 omega naught squared, all divided by 2, and omega high is positive R over L plus the square root of R over L squared plus 4 omega naught squared, all divided by 2. Exact same omega naught, omega low, and omega high that we saw for our band pass filter. Okay, so it's the same thing, same parameters for omega low, omega high. It'll also have the same bandwidth, but in this case, the bandwidth represents the range of frequencies over which attenuation occurs, as opposed to the range of frequencies over which signals passed. If we look at our our phase response, theta h of omega is going to be the inverse tangent of, so if we look up here at our, gosh, went too far, the imaginary part, we can see that we're going to have an omega squared LC minus 1 squared. So overall, just kind of skipping ahead here, omega squared LC minus 1 over omega RC. If I divided my imaginary portion by my real portion correctly, which I believe I did. All right, so those are the two filters, our band stop and our band pass, that can only be recognized or realized using RLC or second order circuits or higher. So what I find to be interesting about this particular configuration, where we're taking the voltage drop over the series combination of the inductor and the capacitor, is it makes it very obvious that this band stop filter is literally just a low pass filter and a high pass filter. Because if we took the voltage drop, so we won't mathematically go through this, but what if we had this circuit? We had a resistor, an inductor, and a capacitor. Here's our in, here's our out. What do you think this guy is? Any ideas? Let's look at it qualitatively, okay? At very low frequencies, so let's look at our impedances. So let's call this guy J omega L, and let's call this guy 1 over J omega C, all right? So at very low frequencies, what does the inductor look like?
A short circuit.
Right, and at very low frequencies, what does the capacitor look like?
An open circuit.
Right, so at very low frequencies, the inductor doesn't do anything at all because it behaves as a short circuit. So it really behaves just like an RC, first order RC filter, where when we're taking the voltage drop over the capacitor, that's going to make this guy a second order low pass filter, right? Excuse me. If we go the opposite route, resistor here, capacitor here, sorry, that should be inductor. In. Here's V out. So at very low frequencies, the capacitor looks like an open circuit. So no signal will get passed through. At very high frequencies, or excuse me, at very low frequencies, the capacitor looks like an open circuit, so no signal will get passed through. And the voltage drop over the inductor will always be 0. At very high frequencies, the capacitor looks like a short circuit, the inductor looks like an open circuit, and so all of the signal gets passed through. So we have here then a second order high pass filter, right? Now the cutoff frequencies for these guys aren't just going to be the inverse of the time constant for RC and RL circuits anymore by any stretch of the imagination, because there are other components in there that are going to change that frequency response slightly, but it's going to be fairly similar. And I think I'm going to give you guys that as a homework problem, is to, instead of just doing our qualitative analysis that we've just done, do a quantitative derivation of the different parameters. But I find it wildly interesting that if we have an identical circuit, we take, it's all just a resistor, a capacitor, and an inductor in series. If we take the voltage drop over the resistor, we get a bandpass filter. If we take the voltage drop over the inductor, we get a high pass filter. If we take the voltage drop over the capacitor, we get a low pass filter. And if we take the voltage drop over the resistor and the capacitor, we get a band stop filter. So it's just really, really neat to me that these 3 elements in series behave in 4 different ways depending on where we take our output voltage drop. All right, so that's all that I had prepared for today. Excuse me. So unless anybody has any questions, I'm going to get your homework set for these circuits prepared today, get it posted and all that kind of good stuff. It'll be due at the end of the quarter like all the other recent homeworks are. And then tomorrow morning, we are going to start talking about 3-phase power. All right, nobody seems to have any questions or anything, so I'll see you guys tomorrow morning.